is Yuzhu Shi, who I really thanks because she was supposed to speak Friday and today, so thanks again for the flexibility. And she's going to talk again about stochastic differential equation of Levy noise. So please, Yuzhu, thank you.
Thank you. So today we'll talk about the geometry and information about say something about the time coupling and also the transition band. So let's start with the backgrounds with a familiar picture. So let's start with this one.
Take the small one.
This is just the last time.
Too scary. Yes, scary glass. So we know that there's two states for the background state, also the high availability state. For the background state, which is really happening in the winter or super cold, so that we can see this phantom just like on the under ice ocean, and also the side of the from this one will have a very less of this, so that the temperature grows very slow. But within summer, like this year is the most hottest year. So the sunlight goes throughout. There's more sunlight, of course, into the available, especially cause some meltdowns. So that this meltdown is darker than the surrounding ice. It makes so much more absorbing about this ice. So the temperature grows higher, and also this biomass of the phenomena also grows. So you can see that the nutrients really because of this melting ice belongs some fresh water, so it also grows higher, so that it is a bistable state within this temperature and also the next state. And sometimes it will cause like the under ice fluid state to this state. So it's our background. And our ODE system is written by the professor in his article, which is for the parameter for the T and U for the biomass for the phytoplankton. And firstly, we add the Gaussian noise. So the first time for the temperature, we use the added noise for the T simulating for the location in the thermal folding. And also for the multiplicative noise is for the U factor 2, simulating the biomass. And here we add a immigration term, so that when sometimes the biomass reaching to negative or reaching to 0, I have a small immigration term like the 2-4 exponent to make sure that the system cannot be negative of the biomass system. So yeah, this is our background. And this come to our main definitions. For one is called the counter function. Here it's like the probabilities that when we start from here, and the probabilities for the first time we reach to the B state rather than reach to the A state. So alongside this commutator function, we can define the stochastic section. Well, the commutator function is equal to 0.5, and instead start from this line, there's 50% for both of arch reach to the same state. So here we define this state as the stochastic separatrix in here.
Sorry, what is this 1/2 isocommutator?
It's the commutator function. It means that the probabilities for the bi-zero states. So if we from this like the function when the QA equal to 0 is that when we start anywhere, there's no probability to finally reach to the 0. And if we start like the QB equal to 1, it means that if you start here, the final result will all come to Q. And will be like the QB equal to
The
0.
Q is so 1/2 is probability. Yes?
Yeah,
Okay.
it's for the probability. Yeah. So when it's equal to 0.5, it means that just have probability for us to both reach to its two states. And in this half, we call it like the isocommutator, and it's this one, and also called the stochastic separatrix. It is the meaning by the probability. And also here we come to define the local thickness. So alongside this picture, and this is the stochastic separatrix, the commutator function equal to 0.5. It is not for the deterministic, it is for the stochastic. And alongside as the normal this one, these two direction, and to calculate for its y's. So that alongside this one and alongside this one, from the 0.4 to 0.6, these two probability of the commuter function will define the mean transition linear sequence by the arc length of this whole length. So for example, like if we start from this line, then there's 40% for us to reach to the E3 state rather than reach to this E1 state. So if we start from this line, there's 60 probabilities to reach this state rather than this state. And this is like the transition of this whole state caused by noise changes. So here's the state changes by the Gaussian noise. So here we use the three different growth rates, B1, like 2, 2.1, and 2.2. And also, as seen in this figure, for the black line is for the deterministic line, and it's crossing the saddle point. The E3 point is the high biomass point, stable point, and this one is the E1 as the low biomass for also the stable point. And this is the saddle point, and this is the deterministic line. And also these three are our stochastic separatrix, and also within the different noise. So you can see that within the noise is increased. You can see that this width of this transition band will be most wider because of the noise increase. Of course, the probability will be more increased. And also within the within the growth rate is increased. Let's move forward to the E3 state. So it is what this figure shows us. And here we link the previous geometry using the time. So the firstly, we use this local normal equation. So this is like the clear function for the local one, and this is for the diffusion part. And to make a one-dimensional Taylor expansion of this one. And the second one is for the draft term, we linearize it. So can write it like this. And here the alpha is the local normal revolution rate. And we bring these equations within these equations and to solve, you can solve this result like a commuter function. And this term looks like the arrow term. It's not for this is arrow, but this term is called the arrow term portfolio. And so by moving forward, we can add the previously definitions of the local thickness. We can define by adding the previous these formulas to here, and also can put this one into here, and also can make this linear relationship. And means that the local y's have a linear relationship within the noise intensity. So we can find this relationship in the weak noise region, and this is for the geometry part. And this one is we link for the time part this theorem. And the Finley-Evans theorem means that the logarithms of the mean first passage time have the inverse square within the noise intensity, so that we link these two formulas, and by animating the noise intensity sigma, we find this relationship is that the logarithms of the mean first passage time have the inverse square relationship within the time within the transition y's, our inverse square. So we by animating the noise intensity. So the positive part for this sentence is that we do not know how the noise intensity is. We can make some prediction about the mean first passage time. Even in the small noise, it is okay. So here's our numerical simulation. We both use the finite difference method and also the Monte Carlo simulation. So we can see that the result fits very good, and these two results shows the similar result. And for the R square is high enough, and this is for the time part to see how it's fitting. And this is very good, shows that the previously duration is can fit this result. And also we use the robust test. For the first figure of the figure A, we try to make sure that if we change the how small noise we need can have this copy below. So we have this test and can see that under the growth rate B1 equal to 2.1, the noise intensity sigma should be less than the 0013, so that our coupling relationship could be fit very clearly. And also the next one is to see that the coefficient in our is very fit within the real one, and the result shows that it's very good. And for the subfigure C shows that if we change the neighborhood about our previously discussion about E1 and E3, because we define it as the ellipse, the ellipse surrounding by this stable point. So if we change the sign of this ellipse, we will finally close. And the result shows that it is stable one. And for the fourth subfigure, because previously assuming that the noise intensity for the both temperature and also both for the biomass is similar. And here we change the 2 times of the biomass and half times of the temperature. And the result is shows that it fits good. But it also have the conditions when we fix this coupling relationship. For the first one is that it needs to happen under the weak noise, obviously. And the second one is that the separatrix should be very smooth, so that we can have the one-dimensional Taylor expansion, so that we could have this repulsion rate alpha. And what I want to mention here is that if this rate of this lambda reaching to 0, it means that alongside this stochastic matrix, the probabilities will be very large. So it means that if you start from here, there's actually it should be the most unstable place under the whole phase plan. But if you look like this one, instead, if you want to escape from here, will be a lot of time. Time will be unlimited, so it cannot be, because of here we are studying the most unstable part, and this is the hardest part we left from here. What about other part? So we must make sure that the separation is smooth. And the third one is that the diffusion structure should also be separable, so that we can animate the noise intensity sigma and format. And previously we have already submitted in the March, and now we are here in revision. So this is our previously work, and I would like to introduce our relevant work. And if you have some questions, just interrupt me and ask, or if you have some ideas, just interrupt me. Yes, our questions will be very, very valuable and precious. So our firstly is working on the Gaussian noise. Here we want to move forward to the Levy noise. So what is the difference between the Gaussian and Levy noise? So the Gaussian noise is more continuously, but the Levy noise is like the jump, and it's very easy to jump outside. So like for example, like in this room, everyone is listening to what I say. And you maybe think about what is the counter function, what is the stochastic separatrix, and what is step by step, how we are making the noise intensity and make the coupling relationship. And this is the Gaussian noise. But if you just notice this board, you say, oh, Gaussian noise, Newton, Apple. I need to change my iPhone. It's very jump of this one. So it is the stable Levy noise, what we use in our daily. This also be widely used in our the AI generating models like the Gaussian noise simulating our this process. But you know, actually we think it's not this. We think about, oh, what is this one? So maybe better to simulate like the some learning noise to have more accuracy result of this generating. Okay, let's move forward to our right now research. So previously we defined the Gaussian noise as the neighborhood as some ellipse surrounding these two equilibrium, and they divide by an unstable noise. Unstable point as the set point. But here because of the learning noise is too much probabilities for us to jump out of the calculation domain. So if we just keep like the previously setting, like just set a very teeny neighborhood, I have calculated, and the probabilities of out of the calculation domain is the 99%. So it's very hard for us to search for global thickness or something else under the previously setting. And yes, the following part is just what I've done for this weekend. So if we have some problem, just ask me. If you found some questions, and just ask me. So we now change the previously the ellipse into the neighborhood. Into the basing. These two basing. So it's previously just in a large free space and only some small two ellipses in here and here. And now we have the whole space is like the previously neighborhood. So from here we define the low statement to high statement is from the boundary without the calculation of domain. Within the calculation of domain is this one. And also from the high state to the low state is just the boundary within the calculation of domain. And here we right now, because of just 2 days, so I just calculating about high to low state this process. A little bit opposite to our previously process because we don't want to see this phytoplankton bloom, but this is the opposite. If we add some biology interpretations, means that we do not want them to go to exist. We do not want them to go to the background state. So here's the high to low state would be here. So the model is just still from the our previous model, and also we have some modifications about the biomass. So previously we used the biomass of the U, and here we use the logarithm of it because it can become more wider when it's near to the 0 point. For the logarithms can extend this area, and also within the immigration terms in case it be negative. And so here we use the Levy noise. It is the Levy noise formulation, and here is for the noise amplitude would be used, and here is for the alpha index stable for the directional stable indexes. Here we set 2 direction for the alpha t for the t side direction, and for alpha y is for the y side direction, and also this is for us to measure how the large tails in this jump. So the alpha stable, this one should be from the 0 to 2. Within the much more smaller alpha means that's the heavier jump tail. And also when alpha equal to 2, it means that it is the Gaussian noise. So by the ecological model, we assume that the alpha t is equal to 1.8, and alpha y is for the 1.4 to better simulate the whole system. For the temperature T is more stable, and for the Y is more unstable rather than the temperature changes for the biomass. So here is what means that the Y direction, because of this one is smaller than this one, so this part has the heavier jump tail. No questions. Okay. So here we define the accessibility coefficient. So we can see in this figure, and also this is constant accessible coefficient, and this part is the Levy jump measure part, and this is for the distribution. And what I want to mention is that it doesn't follow any of the distribution. It's just a by the calculation of our numerical solution. It's not from the like the Poisson distribution or Gaussian distribution. No, it's just the distribution. If we really want to say, I want to say it's like the Olympic dynamic distribution if possible, but it's just very similar, but not this one. And also we can see that there's two direction for the t direction and y direction, and also these two also can combine with the I for the final result. So the direction I is accessible when the coefficient is larger than 0. So when it's larger than 0, it's acceptable, but when it's equals 0, it means that there's two arrows, we don't have these two arrows anymore. So that in this y, we cannot have the useful noise to make us to jump here and to here. But it's only left for the t noise. And so also which part we can deduce that which leading the main jumps is in our this we can see that it's 1.4 because obviously the alpha exponent of this one, index of this one is 1.4 smaller than the 1.8 this one. And we know that the Gaussian noise, we use the mean first passage time to define the which is the mean first time that we reach to the B state rather than go back to the A state. But in here, because we adding some the out of the calculational domain that results, so we need to make some modification. So we here use the mean transition time to make it by adding the out of the calculation domain. So here we firstly define the internal transition rate as the sum of the directional contributions. So we can see there's two of the contributions from the both t side and both y side. And because of for the t side we choose 1.8, and for the y side we choose 1.4. So that this rate could combine with these two. So, and also because of the direction, y direction dominates in the smaller regime. So that may be the y direction leading the more than others. And by the inverse of this, you can define the mean transition time using this one. This is for the mean transition time, and we need to have a relationship within the inverse of the 1.4 as the exponent. But it maybe have some changes because everything is happening under the small noise. Because if we larger the noise, there's more relationship within this one because we need to think about what's really happened if we jump out of the calculation domain. So the result of this one could not only combine with the really happened caused by the 1.4 and 1.8, these two in the calculation domain, but could combine with the results that jump out of the domain. And with if that time will be still 1.4, our previously result is not. So let's continue. This is for what we define the transition probabilities and thickness. So firstly, we define as the counterfunction like the 0.5 from the 40% to 60%. But here, if we still like what I previously discussed, if we still remain the calculation domain like those two teeny ellipses, will be very hard for us to reach to the final destination. So here we define as the new counterfunction, like if we start this point, the first time we reach to the B result rather than go to the jump out of the calculation domain. We count as the 50% of that our cognitive function is. That's why we use the high to low side. If we use the low to high side, it means that we first time to jump to the A rather than jump out of the calculation domain. So that's the totally quite the different thickness line. And here we use the high to low, so we use the B for the reference. but we will to try if we move forward to A what will really happen. So we also define for the 2-1, for the local thickness, we abstract this point alongside the saddle point, and from the global one, we abstract this point from the global phase space. And also this is the present, he's famous.
Yeah.
A little bit nervous to say this part.
Just continue, so everything is
Here
correct.
the name.
This is his results,
Everything is correct.
and this is our derivation result. And we can see that we still have a linear relationship within the noise altitude and also the local thickness. So by also eliminating the noise intensity, you can have these two formulas. For this one is for the local one, so alongside the saddle node, we can find this result. And for this one is for the global one. So that if this system is clean enough, it just means that we can abstract this result from the whole system, then we can show the global one. But most of the time is that the local one is obviously because we can derive it, it must relate to one. If we want to derive it, I will derive it later, just up to the time. And but this one is very hard for us to get from the whole phase space. So
You do just one moment here about the Ilya article. Yeah, as we know, it's small noise intensity in the stochastic differential equations. We use large deviation theory for the scalings, and in case of Levy, it's famous. They start from earlier, since I know Ilya, yeah. Everyone is using small noise intensity, such as scaling. No
That's was
more.
interesting.
You know no more. There's like fundamental paper that they are told they change well potential in different types, or one-dimensional, two-dimensional, steep, and even the sine cosine. You had some kinds of no, cycle. It was on paper for the cycle, so they didn't not attractors, but for the cycle, but still remaining this. Yeah, that was a result.
Okay. Please continue.
no questions? Okay. So this is our first figure, and better explain this one. So if you found any problem and mistake, so here's what we prove why the y direction leading the main direction, because of here you can see that and most of it's y took this place and just less of the t took this place. And also here's the from the low side to high side, and high side to lower states. For the low to higher, it's much more complex because there's too many jump out of the domain, like the 50%. Even if we define like the two boundaries where our small teeny neighborhood lives, but also have too much jump out of the calculation domain. And also this is the high to low result. We can see the result is like the 20% of just we jump out of the calculation domain. So and basically really the reason why we choose a high to low, even though we first calculate about low to high. The reasons why we cause about this result is because there's even if we use the immigration term, even if we use the logarithm of the biomass this part from the u change to the y to s to logarithm, but there still have too much one jump that we can jump out of the calculation domain. And it's the relationship within this one. And here's for the time scaling. So we can see this one is, we want to see that it is reference as the negative 1.4, and we extract these 22 noise values from here to here, and you see that this slope is like the negative.
5 minutes. 5 minutes. I'm telling you, you have 5 minutes. Don't do the best.
So here's the 1.4, and here we can see that if we larger this noise intensity, here like the 0018, the result will be changed. Because we want to see it like this one, because it's leading by 1.4 for the y directional. But why we change here, well here we'll change like the t directional, because of there's not only for the calculation of the domain just I talked about, is too much will jump out of the calculation domain. And for this one, it's most of the result will jump out of the left t boundary. So it will cause this result. And this is for the time side. But it's for the geometry side. You can see that it's the transitions from here. So this is the most probability, so that even if we start from these two boundaries, it's very high probabilities for us to stay in this space rather than jump out. So in here, there's more probabilities to jump these boundaries rather than jump out. But with the noise intensity increase, you can see there's to this side. So when it means that the whole system is more unstable, so that it's very hard for these two to connect at a connection bridge. And firstly, we define as the global thickness as the conditional commutative function. Is that I want to happen both the QA and QB, and when these two happen, what's the probabilities of QB really happen? But you can see like this one, so it's very hard to abstract what is the stochastic separations within this one, and A and B they cannot catch the bridge from A to B, just jump out of the calculation domain, even if in this figure, like that thing. So that's what we still try to make sure how to calculate this one. But this is our current calculation about this. And this is for the local one. Firstly, for the global, and this is for the local one, is more stable. Just like we previously the Gaussian noise like this. Within the noise intensity increase, that the width of this one is broadened. And also will have smooth within this one, more proportion to the E3. And this is the same result within our Gaussian noise. So yeah, that's the fitting. We also see that the linear relationship within the noise intensity and also the global wax. And also we try to make sure if this relationship is equal to 1. So we want to see the result is equal to 1. So we try these different windows of the noise intensity or amplitude in the Levy noise. So we find this point will be the most perfect like this result and very related to 1. But if we come through the coupling relationship like we previously do, we can see the problem. So for the noise in the noise part, we need to make sure that noise is small enough so that we can fit like the 1.414. If we make the much more smaller noise, we'll like to very close to 1.4, or just equal to 1.4. It's good. But we need to be sure that they are under the same condition. So that if this one is like this one, it's like the noise intensity like this one. Here, it's very small noise intensity, but if we calculate like the geometry part, it's much larger. It's much larger than the noise. So let's come to our problem right now is the noise intensity is smaller than the grid, what we calculate. And if we make the grid is small enough, it takes too much long time, it's too complex to catch. And I also modified like, I'm wondering if like other algorithms, we also know that we cannot find the global thickness in this side and this side, just along of the stochastic separations. So that when I make this grid along side will be smaller. But right now the result is not very good. And I'm still exploring what is the final method to solve this. Like the PNN's method, but maybe a little bit too complex because just for the two-dimensional system and still exploring for this one. So this is our current result. for the fit is this like this one, not too much to one, and this is like this one, not too much to one, and this is like this. But we prefer to see that it's negative 1.4. And finally, I want to show two of the clean models because the previous model is not symmetric and we use the anisotropic noises to make it more complex. And here is the clean models and we use isotropic noise and also they are two symmetric. So by this one, we can see that the result is very nice for the noise like this one and the global thickness within the noise amplitude is for 1 and final cognate relationship is like this one. And this is for another clean and anisotropic benchmark. Under this system, you can see these two are very clear and the result shows it's very related to what we want to want to see. So yes, here's come to the end of my speech. So this one is for our previously work about the Gaussian noise, and this is our current work about changing the previously coupled relationship within the Levy noise. And here's what we meet some problems within our current work, and this is and also the conditionals for this one. We need to make sure that weak noise, regular layer, and also regular and traceable transition layer, and diffusion coefficients so that we can eliminate the noise sigma. And and in here we need to make sure that the event match. So we need to make sure that the Y jump and T jump, this noise is event match, and also make sure that the noise amplitude windows are similar. So yes, it comes to the end.
Any questions?
Directional selection, very interesting. Could you say a little more? So it's one dimensional, so you have a left or right or two dimensional?
It's two-dimensional.
Three-dimensional, okay.
So the noise will jump from this part and also this two direction. So in this y direction for
So the vertical and the horizontal,
it's like the coordinate.
left and right, okay. So,
Professor Don, we did some simulations when we see that we cannot find the layer in between. We make like not like angle, but rotation, and we add such term in rotation, not just jumping in such a directions, but it doesn't help us to
Yes, because in this graph, to make sure that the graph is like just strictly from the y side and t side. But if we rotating this two, like if we E1 to E3, like it's rotating like this one, and there's two results.
But yeah, we can make just not rotation in.
Because the
and
result
it's also for small noise, right? Okay. That's
Yeah.
Any more questions? Well,
How do you choose the alpha parameters in your model?
For the about 1.2.
Yeah, the 1.4 and 1.8.
For this one, it's better to simulate the richer. It's better to for the biomass.
so this comes from data because actually it was similar was my question. So why Levy or not? Why Levy? Why Gaussian? So you get this from data. This is
It was like a biological explanation. Biological explanation is such because temperature is changing slow and biomass is faster in these like two coefficients, and it was proposed by biological model. And even we had the problem maybe when we change alpha, its result depend on. But we stick on such alpha because this people from biology will ask why you change its reason biological climate, how temperature and biomass is changing in time. This coefficient pure.
But if you want to change like 1.9 or 1.3, it's okay. Just
in terms of math, because we know that less than 1 is crazy happening, like 0.5, yeah, but
And I think it is a very good thought for us. What if we can change this from the 2 to like 1.8 so to show, to see how it changed from the alpha stable, it changes.
I wonder if you could like analyze data, I don't know what type of data would be relevant to estimate, I don't know, the tails of the distribution or to get these
we would
parameters.
not rely just on the collision, but search for some data and see data distribution or whatever.
Nicola, then I think we go because we are a bit long.
I was wondering if there are some hopes to move this to higher dimension, like in 3D, then you have maybe chaotic attractors, and like it's much more complicated, especially if you do a geometric approach, because the separatrix is not smooth. But maybe with these kind of stochastic separatrix, then you have some fuzzy thing, and then things are smooth again. So I don't know if you have plans to go.
Yes, in here. So it decides on how we observe the transition band. So firstly, we just observe the transition band like this one. So we have the linear relationship with this. And if we use the like this one, and if the slope is for 1 because there is a linear relationship. But it's still some cases about, and even under the Levy noise is stronger. It's well the same result. Very quickly. So but if we observe like this one, we just observe like if we firstly observe this one, and then we observe like this one. So if we see from here, so how it's related to speed, and this time will become rather than we firstly want to this one become. So this is what we want to explore. This is for the and we want to explore this from high dimensional, and this is combine this like this one because it decides what you observe of observation exponent. So maybe, and we had this relationship to move forward to the high dimension. But our key problem is to fix why the noise is larger, it's smaller than the grid. So we need to fix how we can abstract the global thickness. Yes.
Problem global thickness for such a model, because no model works because very nice gradient system with zero potential synergic and everything is working nicely. But when we move for non-gradient system, it's local thickness, it's okay, but global one, we have to work on such a condition.
I think personally I have more questions, but maybe we can continue separately. So, okay, thanks again.